A Nimitz-class aircraft carrier weighs 100,000 tons. It runs on 2 nuclear reactors producing more than 260 megawatts of propulsion power. It can sustain 30 knots, roughly 35 miles an hour, day after day, without refueling for decades. It carries 90 aircraft and more than 5,000 sailors. Its radar and sensor suite reaches hundreds of miles in every direction. By any measure, the Nimitz-class is the most capable surface warship ever built. And right now, trailing 2 miles behind that ship in the dark water of the Western Pacific, there is a cable. A thin hydrophone cable, roughly the diameter of a garden hose, stretching back a full nautical mile, sometimes more, behind the hull. No armor, no propulsion, no weapons, just wire and sensors drifting in the carrier's own wake. And the moment that cable goes into the water, the entire strike group, destroyers, cruisers, supply ships, submarines working in coordination, slows to roughly 15 knots, half speed. The most powerful surface fleet in the world, cut in half because of a wire. Here is the paradox the title promises. If the Nimitz-class has the most advanced sensor systems afloat, why does it depend on something that looks like it belongs on a fishing trawler to find what it is actually afraid of? The answer is not what most people expect, and it runs deeper than sonar physics. It touches on why the quietest, cheapest submarine in a rival navy's inventory can force a $9 billion carrier group to make a choice it cannot avoid. Stay with this, because the trade-off at the center of that choice is what shapes every carrier transit across the South China Sea right now. To understand what the cable does, start with what carrier strike groups actually fear in the Pacific today. The nuclear submarine, fast, deep-running, nuclear-armed, is the obvious candidate. But naval planners at the Pentagon rank the diesel-electric submarine as the more operationally disruptive threat in the near to medium term, specifically in the confined, shallow to medium depth waters of the Western Pacific littoral zone. Here is why. A modern diesel-electric boat running on battery power, what submariners call AIP mode, or air-independent propulsion, produces almost no acoustic signature, no reactor, coolant pump cycling, no steam turbines. The electric motor turns the propeller with near zero vibration. A well-maintained boat of this class, moving at 3 to 4 knots on battery, is acoustically quieter than ambient ocean noise in many sea states. It is, in practical terms, a hole in the water. The People's Liberation Army Navy operates over 60 diesel-electric submarines today. The most capable are the Type 039A and the newer Type 039C boats, sometimes called the Yuan class in Western assessments. These boats carry U-6 wake-homing torpedoes and CJ-18 anti-ship cruise missiles. Their battery endurance at low speed lets them hold a patrol position for days without snorkeling. Beijing shipyards have been commissioning these boats at a pace that draws consistent attention from Indo-Pacific command planners, roughly 4 to 6 hulls per year across the past several years. The carrier strike group, moving at speed, faces a detection problem that is fundamentally physical. The Nimitz-class hull carries an AN/SQS 53C bow-mounted sonar, a powerful active and passive system. At speed, the flow noise generated by water rushing past the bow dome, combined with propulsion and machinery noise from the ship's own systems, creates what acoustic engineers call self-noise. That self-noise floor rises sharply with speed. Above roughly 15 to 18 knots, the bow sonar's effective passive detection range against a quiet diesel target compresses dramatically. The very speed that defines the carrier's tactical flexibility also makes it partially deaf. The escorting Arleigh Burke class destroyers carry their own AN/SQS 53D bow sonars and AN/SQQ-89 integrated ASW combat systems. They are far quieter than the carrier, and their hull sonar performance at moderate speeds is substantially better. But in a structured threat environment, one where a quiet submarine has time to position itself ahead of the group's track, the destroyer's hull sonar coverage still leaves geometric gaps, particularly off the carrier's quarter and astern, where propeller noise and the carrier's own acoustic wash create a shadow. What fills that shadow is the TB-29A towed array. The TB-29A is a thin-line array, roughly 900 feet of hydrophone sensors in a neutrally buoyant cable, towed on a wire that extends 1 nautical mile or more behind the host ship. Because the array is separated from the ship's own machinery by that long tether of water, its sensors operate well below the ship's self-noise floor. A carrier or destroyer towing a TB-29A at 15 knots can hear things its hull sonar cannot even approach at that same speed. The physics is simple. Water between the ship and the sensor acts as acoustic isolation. Distance kills self-noise. The longer the array and the slower the tow speed, the better the signal-to-noise ratio. The system is not magic. It is geometry and physics working together in the one configuration that makes passive detection viable against a quiet target. Most people assume the carrier's hull sonar is its primary ASW sensor at range. It is not. At transit speeds, the towed array is. That distinction matters for everything that follows. Here is where the layers of the trade-off open up. A diesel submarine hunting a carrier strike group does not need to be close. A U-6 torpedo has a range of roughly 25 to 40 nautical miles in its anti-ship configuration. A CJ-18 cruise missile reaches substantially farther. The submarine does not need to close to visual range or even close approach sonar range to engage. It needs to get within weapons employment range without being detected first. The towed array changes the geometry of that problem significantly. ATB-29A operating optimally can detect a quiet diesel-electric submarine, depending on sea state, water temperature layering, and the target's speed, at ranges of 20 to possibly 40 nautical miles in favourable conditions. That is the outer edge of many torpedo envelopes. Detection at that range gives the strike group time to vector an MH-60R Seahawk helicopter, reposition an escorting Arleigh Burke, or coordinate with a Virginia-class submarine operating ahead of the group to develop a firing solution before the threat closes. Without the towed array, operating at 30 knots with degraded hull sonar passive performance, that detection range compresses. The group may not know the submarine is there until it is well inside weapons employment range. At that point, the options narrow sharply. So the cable matters. The question is what it costs. The cost is speed, and speed is not a minor operational variable for a carrier strike group. It is the central one. A Nimitz-class carrier at 30 knots covers roughly 840 nautical miles in 24 hours. At 15 knots, it covers roughly 360. On a Pacific transit from Pearl Harbor to the Philippine Sea, a common operational movement covering roughly 3,500 nautical miles. The difference between a sustained 30-knot and 15-knot average is measured in days, not hours. 3 days, 4 days. In a developing crisis, that gap is not abstract. It is the difference between being on station before a situation hardens and arriving after it has. There is a second layer. Deploying the TB-29A at speed above 15 knots risks cable damage or loss. The hydrodynamic forces on the cable increase with the square of velocity. Running at 25 knots with a deployed array risks kinking the cable or losing the array body entirely. The cost of a single TB-29A array runs to several $1 million. Modest against a $9 billion hull, but the dollar cost is not really the point. The array only delivers its detection advantage at low speed. Speed and detection are not independent variables. They trade directly against each other. Put yourself in the carrier strike group commander's position. You have intelligence suggesting a possible submarine patrol in the area you are transiting. You can run fast and accept degraded passive detection, relying primarily on your Arleigh Burke escort's hull sonars and on a P-8A Poseidon Maritime Patrol aircraft working ahead of your track. Or you can deploy the array, slow to 15 knots, gain your best available passive detection, and accept the transit delay and the vulnerability window that comes with operating slowly in a threat area. Neither option is clean. What most briefings skip is that slowing the entire group creates its own tactical problem. A slow carrier strike group is easier for a submarine to track and easier to intercept. A submarine commander who knows a carrier group transits a choke point at 15 knots has a simpler targeting problem than one facing an unpredictable 30-knot group that may change course without warning. The cable that provides the ears also partially removes the evasive option the carrier's speed would otherwise enable. That is the actual paradox. The system that most improves detection also reduces the group's ability to outrun a developed targeting solution. The TB-29A is not the only sensor in play. A full carrier strike group conducting a deliberate ASW transit deploys a layered detection architecture. P-8A Poseidon's fly barrier patrols ahead of the group, dropping sonobuoy patterns to sanitize the approach path. MH-60R Seahawk helicopters from the carrier's own air wing. Typically 4 to 6 ASW-configured Seahawks in a Nimitz air wing. Work close in barriers, dipping their AN/AQS 2-2 airborne low-frequency sonar systems into the water column on a rotating schedule. An escorting Virginia-class submarine, operating independently ahead of the group's track, provides the one sensor platform that can genuinely pursue and engage a quiet diesel contact at depth. The towed array fits into this architecture as the carrier's own long-range passive sensor, the system that gives the group's flagship some independent detection capability rather than relying entirely on escorts and aviation assets. A carrier without a towed array deployed is acoustically dependent. A carrier with the array deployed is a participant in its own defense, not just a target waiting for its screen to call out threats. What this system exposes is a structural asymmetry in carrier strike group design. The carrier is built for power projection, putting aircraft over targets, sustaining air operations, maintaining presence. Its ASW capability is fundamentally a retrofit consideration. The 29A partially corrects that imbalance, but it does so by imposing a constraint that runs directly against the carrier's core operational identity, speed. Now to the economics, because the cost asymmetry here is one of the starker ones in modern naval competition. The TB-29A program cost is classified in detail, but publicly available contract data and budget justification documents suggest individual array systems in the range of $2 to $5 million per unit. The P-8A Poseidon Maritime Patrol aircraft that supports the carrier's ASW barrier costs roughly $230 million per airframe. The MH-60R Seahawk helicopter costs roughly $30 to $40 million. An Arleigh Burke class destroyer is priced at roughly $2 to $3 billion per hull in recent contract awards. The submarine those systems are searching for, a Type 039A Yuan-class diesel-electric boat, costs Beijing's naval planners roughly $200 to $300 million per hull by open-source estimates. That is 1/10 the cost of a single Arleigh Burke and roughly 1/30 the cost of a Nimitz-class carrier. The arithmetic is clear. One relatively inexpensive submarine, properly positioned and handled, forces a $9 billion carrier and its multi-billion-dollar screen of escorts to slow, deploy aviation assets, coordinate across multiple platforms, and accept a transit schedule that may be days longer than an uncontested passage. The resource investment required to find and neutralize that submarine exceeds its cost by an order of magnitude. This is not a new observation. Naval planners have grappled with it since the Cold War, when Soviet Foxtrot and Kilo-class boats posed similar problems for carrier groups in the Atlantic and Pacific. What is new is the scale of the modern challenge and the geographic specificity. Beijing's submarine fleet has grown substantially in both numbers and capability across the past 2 decades. The Type 039C boats entering service now incorporate noise reduction measures and AIP systems that make them meaningfully quieter than the previous generation. And Western Pacific geography, with its island chains, shallow seas, and predictable transit routes through choke points like the Luzon Strait and the Bashi Channel, favours the defending submarine over the transiting surface group. Here is the take that will probably draw some disagreement. The towed array is not really a solution to the diesel submarine problem in the Western Pacific. It is a management tool for an asymmetry that the carrier's design does not fundamentally resolve. The carrier's speed advantage over a slow diesel submarine is real, but that advantage only exists if the carrier is willing to give up the detection capability the towed array provides. The moment the carrier deploys its best ASW sensor, it surrenders its primary tactical response to a developing contact. That is not a failure of the TB-29A system. It is a structural feature of carrier design that no cable can fully correct. This is where the loop closes, and where the picture is more complicated than the cable paradox suggests. The towed array deployed by the carrier is not the TB-29A in isolation. The full designation is TB-29A Broadband Thinline Array, and it operates in conjunction with the ship's AN/SQQ-89AV15 integrated ASW system, which fuses inputs from the hull sonar, the towed array, and external sensor reports from helicopters and maritime patrol aircraft into a single tactical picture. The array's passive detection data feeds a signal processor that applies beam-forming algorithms to separate target signals from ambient noise. What the sonar operator sees is not raw audio. It is a processed display showing bearing lines to acoustic contacts, updated in near real time, at slow transit speeds in favourable acoustic conditions, specifically in deep water with a well-defined sound velocity profile. ATB-29A towing at 12 to 15 knots can generate detection quality data on a quiet target at ranges the hull sonar operating at the same speed cannot approach. The geometry works because the array's length, 900 feet of sensors, lets it form tight acoustic beams. A single hydrophone hears noise from all directions equally. An array of hundreds of hydrophones, separated by known distances and processed with phase delay corrections, can resolve a target bearing to within a fraction of a degree at long range. That bearing resolution matters for one specific reason. It is what allows the carrier to hand off a contact to an MH-60R Seahawk before the submarine closes to weapons range. The helicopter, with its dipping sonar and lightweight MiG-54 torpedoes, is the prosecuting weapon. The towed array is the cueing system that gets the helicopter to the right piece of ocean before it is too late. The chain runs TB-29A detects a bearing anomaly at long range, AN/SQQ-89A, processes and classifies the contact, helicopter assets are vectored on a cued intercept, AN/AQS-22 dipping sonar refines the contact and develops a firing solution. The submarine's options compress. No single element of that chain can complete the engagement reliably without the others. If the carrier is running at 30 knots without the array deployed, the first link does not exist. The helicopter cannot be cued on a contact. The carrier cannot detect. The P-8A working barrier ahead of the group may have the contact, but the P-8A covers a finite area and gaps in its sonobuoy barriers are real. The commander who chooses to run fast accepts those gaps. The commander who deploys the array and slows to 15 knots closes them, but opens a different one, the temporal gap between where the group is and where it needs to be. There is one more layer here that rarely gets discussed in general treatments of carrier ASW. The Virginia-class attack submarine operating ahead of the carrier group changes the calculation in a way the surface assets cannot replicate. A Virginia-class boat, at roughly $3 billion per hull, is the one platform that can pursue and engage a quiet diesel contact in its own medium. It does not need the carrier to slow down. It does not need a favorable sound velocity profile. It can follow a diesel submarine into shallow water, into thermocline-disrupted environments, into areas where towed arrays and hull sonars are acoustically compromised. In a well-structured ASW transit, the Virginia-class submarine operating in coordination with the carrier's aviation assets and towed array represents a layered detection and prosecution architecture that no single quiet diesel can reliably evade. But Virginia-class boats are finite. 11 currently in commission as of the mid-2020s, with the Block V boats now entering service and a construction program that has struggled to meet its planned delivery rate. The submarine industrial base in the United States has been a point of consistent concern in congressional testimony and Pentagon budget justifications across recent years. The Block V Virginia is budgeted at roughly $3.4 billion per hull. The construction pipeline faces competition from the Columbia-class ballistic missile submarine program and from the ACUS commitment to provide at least one Virginia-class hull to Australia under the Submarine Pathway Agreement, a commitment that draws from the same limited production capacity. The arithmetic of the builder's challenge is straightforward. If the carrier strike group's best ASW asset is the Virginia-class submarine accompanying it, and if the number of available Virginia-class boats is constrained by production rate, then not every carrier group transit in the Pacific will have that asset available. Some transits will depend primarily on the towed array, the P-8A barrier, and the Seahawk helicopters. On those transits, the cable trailing behind the carrier carries more weight than at any other moment. The strategic cost of the trade-off extends beyond individual transits. A carrier strike group constrained to 15 knots for ASW protection is not just delayed. It is in a different operational posture than a group running at speed. The Nimitz-class carrier conducting flight operations typically needs to steam into the wind at a speed that generates adequate wind over deck for aircraft launch and recovery. In calm conditions, that means the carrier may need to make 25 to 30 knots just to generate adequate deck wind for the F/A-18 Super Hornet or F-35C to launch from the catapult. If the group is constrained to 15 knots by the towed array deployment, flight operations depend on a wind component from the environment that may not always be present. The cable and the flight deck schedule are not independent variables. This is a detail that stays with you when you go through the operational records. ASW doctrine often treats the towed array as a deployment when needed tool, something the group pulls out for threat transits and stows when it wants to operate freely. In practice, the interplay between the carrier's flight operations requirement and its ASW posture creates a scheduling tension that ship captains and strike group commanders manage daily. Heavy air operations push speed up. ASW threat environment pushes speed down. The two requirements pull in opposite directions, and the commander resolves that tension with judgment calls that do not appear in any doctrine document. The crew load is real. An Arleigh Burke class destroyer operating as the primary ASW screen for a carrier group maintains a watch cycle that places significant demands on its sonar technicians and ASW coordinators. A typical deployment cycle for an Arleigh Burke in the Pacific runs roughly 7 to 9 months, with operational tempo that has increased as Indo-Pacific Command has expanded its presence requirements. The 2016 collision incidents involving USS Fitzgerald and USS John S. McCain, both Arleigh Burke class destroyers, drew congressional and Navy attention to crew fatigue and watch-standing sustainability in ways that connect directly to the operational rhythm described here. The technical capability of the towed array and the ship's sonar systems is only as good as the watchstanders who interpret their output. And those watchstanders operate on rotation schedules that sustained high-tempo compressors. What do you think? Does the Navy's current ASW architecture put too much of the detection burden on a small number of human operators running around-the-clock watch cycles, or is that a problem that better automation can solve in the near term? That question is not rhetorical. The answer shapes where the next generation of ASW investment goes. The geostrategic picture frames the urgency. The Western Pacific is not a symmetric operating environment for a carrier strike group. The island chain geography. The first island chain running from the Ryukyus through Taiwan and the Philippines creates a series of choke points through which any carrier moving from the open Pacific toward the South China Sea must pass. The Luzon Strait between Taiwan and the Philippines. The Bashi Channel to the south. These are constrained passages where the geometry of towed array detection changes significantly. In shallow, constrained water, acoustic propagation becomes unpredictable. Temperature layers and bottom topography scatter sonar energy in ways that degrade detection ranges. The towed array that performs reliably in open deep water does not perform identically threading a 100-mile wide strait with variable bottom depth and heavy merchant traffic noise. Beijing's planners understand this geography thoroughly. The positioning of planned submarine bases on Hainan Island, inside the South China Sea, gives diesel-electric boats operating from that base access to patrol areas without having to transit the choke points that a carrier group must use. A Yuan-class submarine that takes up a patrol position in the Luzon Strait or the Bashi Channel while the carrier group is still approaching from the east has a significant geometric advantage. It is already inside the water the carrier must transit. The carrier group's towed array will be working in the open Pacific as it approaches, in conditions where the array performs well. The moment the group enters the strait, those conditions change. The P-8A Poseidon working ahead of the group becomes the primary sensor in those constrained passages, flying ASW barriers across the strait's width and sanitizing the track before the surface group enters. But the P-8A has an endurance limit, and the time window between initial barrier sanitization and carrier group transit must be managed. A submarine that is patient, that moves slowly on battery, below the thermocline, during the gap between P-8A sweeps, may not appear on any sensor until the geometry has already closed. One more level down. The crew aboard a diesel-electric submarine running on battery in a patrol position in a shipping lane can simply wait. It does not need to maneuver. It does not need to emit. It can hold depth and course and let the carrier group's own noise signature drive the geometry to it. That passivity is itself a tactic, and it is one the towed array is specifically designed to counter. By detecting the submarine's own low-level machinery noise before the carrier has closed the range enough to matter. If the array is deployed, the carrier is slow but listening hard. The submarine's patience advantage erodes as detection range extends. If the array is stowed and the carrier is running fast, the submarine's patience advantage is intact because the carrier's hull sonar performance at high speed cannot match the threat. The commanders on both sides of that geometry know this calculation. It is not secret. It is physics and doctrine, and both Navy's planners have read the same literature. The resolution of the loop. The cable trailing behind the Nimitz-class carrier is not a compromise or a workaround. It is the best available solution to a detection problem that the carrier's hull design cannot solve at transit speed. The self-noise of a 100,000-ton ship moving through the water at 30 knots is a physical constant. You cannot engineer it away without fundamentally redesigning the ship. The towed array is how the Navy manages that constant, by placing sensors far enough behind the ship that the ship's own noise no longer drowns the target. The paradox of the title resolves to this. The carrier trails the cable precisely because it is so large, so fast, and so loud at speed. Its capabilities are the source of its blind spot, and the cable is the instrument that partially addresses that blind spot by accepting the constraint those capabilities make necessary. But the deeper layer, the one the cable cannot fix, is the trade-off between detection range and transit speed that the cable's deployment imposes. That trade-off exists because the carrier's primary tactical asset is its speed, and the system that most improves its ASW detection removes that asset for the duration of its deployment. The commanders who manage this trade-off in the Pacific today do not have a clean answer to it. They have doctrine, experience, and layered sensor architectures that reduce the risk on either horn of the dilemma. The P-8A Poseidon forward barrier provides detection coverage the carrier does not need to slow for. The Virginia-class submarine operating ahead of the group pursues and prosecutes contacts the surface ships cannot reach. The MH-60R Seahawk provides close-in dipping sonar coverage that fills gaps in the towed array's geometry. Together, these systems allow the strike group commander to make a judgment call, deploy the array and slow for the highest threat transits, run fast with aviation-based coverage for lower threat open ocean passages, rather than being forced to choose between deaf and slow at every moment. What has changed in the Pacific is the frequency with which the highest threat category applies. As planned submarine numbers grow and as the capability of those boats improves, the transits that demand towed array deployment, that demand the 15-knot posture, become more common. The cable goes into the water more often. The time cost accumulates. Here is the part that took a while to sit with clearly. The strike group that deploys its towed array most aggressively, most consistently, is also communicating something to any opponent monitoring its movements. A group at 15 knots with a deployed array is not a group rushing to respond to a crisis. It is a group in a deliberate, methodical ASW posture. The posture itself is readable. A commander who needs to sprint, who needs to get the carrier on station fast, accepts the acoustic risk of high speed because the alternative is arriving too late to matter. The submarine knows this. The towed array's deployment schedule tells any watching adversary something about the commander's assessment of threat level and operational urgency. Intelligence, in that sense, flows both ways from the cable's presence in the water. The balance of force picture in the Pacific today reflects all of this. The United States Navy operates 11 carrier strike groups centered on 10 Nimitz-class and 1 Gerald R. Ford-class carrier. The Gerald R. Ford, which entered service in 2017, carries the AN/SLQ 6-1 lightweight tow system in addition to standard towed array capability, an updated towing architecture that improves handling and deployment speed. Future carriers in the Ford class are expected to incorporate further ASW system improvements as the class matures. But the Nimitz carriers, which will form the backbone of the carrier fleet through the late 2030s and beyond, carry the TB-29A in its current configuration, and the trade-off it imposes remains unchanged. Beijing's naval planners watch the carrier group's transit patterns closely. Satellite reconnaissance, signals intelligence, and open-source vessel tracking all contribute to a picture of how American carrier groups move through the Western Pacific when they deploy their arrays and what speeds they maintain on different track legs. The plan's counter-carrier strategy, centered on the DF-21D and DF-26 anti-ship ballistic missiles that Western analysts call carrier killers, is not designed to defeat the carrier in a close-in engagement. It is designed to hold the carrier at long range, outside the aircraft's strike radius, and to make the transit to that range sufficiently costly that the carrier's presence cannot be assumed in a crisis. The submarine threat is one layer of that strategy, designed to complicate the transit phase before the carrier even reaches its operating area. The towed array is one piece of the American response to that pressure. It does not resolve the larger strategic challenge, but it addresses one specific and operationally consequential part of it, the detection gap that the carrier's own speed and noise create in its passive sonar picture. For the price of several $1 million per system and the operational cost of reduced transit speed, it gives the carrier's commanding officer a detection tool that the ship's hull geometry cannot otherwise provide. The Arleigh Burke destroyers in the escort screen carry their own towed arrays as well. The TB-16D fatline array, used for low-frequency passive detection at longer ranges, and the TB-29A thinline array for higher frequency performance. A fully deployed carrier strike group running in ASW posture presents a layered curtain of towed sensors, hull sonars, helicopter dipping systems, and forward-operating submarine coverage across a very large ocean area. The quiet diesel-electric submarine operating against that architecture is not dealing with one sensor. It is dealing with overlapping coverage from multiple sensor types, multiple platforms, and multiple engagement options. Its task is complicated, but not impossible, particularly in the acoustic environment of shallow, confined passages. The numbers that matter here are not just the dollar figures on individual systems. They are the ratio of available ASW platforms to the area that needs to be sanitized, and the number of submarine contacts that need to be tracked simultaneously. One Virginia-class submarine providing close support to a carrier group is one submarine. If planners deploy 3 or 4 diesel-electric boats to contest a single carrier's transit corridor, the geometric coverage problem expands. Each additional contact requires additional sensor and prosecution resources. A strike group commander already managing one possible contact while trying to maintain flight operations and keep the carrier on schedule is in a very different position than one managing a clear water picture. That multiplication of contacts is not academic. It is how an asymmetric approach to carrier denial works in practice. Not by defeating the carrier in a single engagement, but by imposing a resource and attention cost that degrades its operational timeline, complicates its routing, and forces it into postures that delay its arrival. Comment why yes or no. Will the next generation of undersea drones, autonomous unmanned underwater vehicles deployed ahead of the strike group, eventually replace the towed array as the carrier's primary passive detection tool within the next decade? The closing question for this episode is the one the commander actually faces. A carrier strike group is approaching a high-threat transit corridor. Intelligence suggests at least one diesel-electric submarine may be operating in the passage ahead. The carrier is 48 hours behind its planned schedule. A developing situation in the operational area means that arriving on time matters. Presence matters, and a carrier that arrives 2 days late may arrive after the moment at which its presence changes anything. The commander can deploy the TB-29A towed array, slow to 15 knots, and take the best available passive sonar coverage of the passage, at the cost of arriving 36 hours later than the delayed schedule already requires. Or the commander can stow the array, run at 28 knots with P-8A Poseidon barrier coverage and Seahawk close-in support, accept the degraded towed array detection capability, and arrive roughly on schedule, at the cost of a detection gap that may or may not be exploited by a submarine that may or may not be there. The math does not resolve that choice cleanly. The detection range advantage of the array versus the arrival time cost of deploying it are not commensurable quantities. One is a probability. The probability of detecting a submarine contact early enough to prosecute it before it reaches weapons range. The other is a certainty. The hours it takes to cover the distance at 15 knots versus 28. Commanders weigh those quantities with judgment shaped by intelligence assessments, operational experience, and the specific stakes of the mission they are executing. What the cable behind the carrier tells you, in the end, is what the carrier is afraid of. Not the carrier-killing missile flying at Mach 5 from a coastal launcher, but the quiet, patient boat 300 feet below the surface that does not need to be fast, does not need to be loud, and does not need to win a fight. It only needs to survive long enough to make the geometry work in its favor. One cheap submarine, one expensive dilemma, and a cable trailing behind the most powerful surface warship ever built, telling anyone watching exactly what the carrier thinks is down there. Here is the question worth sitting with. A commander who deploys the array and crawls gives up time. A commander who runs fast gives up detection range. Both costs are real, but only one of them is recoverable. Which one is that? And does it change your answer depending on what is waiting at the other end of the transit? Tell us where you land in the comments. And if you want to go deeper on the Virginia-class production problem and what it means for Pacific coverage, that thread runs further than this episode had room for.